Hello, I am Mahil Parmar from OV Sarjapur, and today I am presenting my paper, which is Vehicular CO2 Emission Capture Technology. As we can see in the front screen, there are two images. The first one represents pollutions. As we can see that pollution emerges from industries, burning of fuels, and automobiles. In the second image, we can see its effects, how it leads to global warming and natural disasters such as cyclones, droughts, and floods. So, as we all know, that carbon dioxide emissions are increasing at a rapid rate. This image shown to us by ourworldindata.org shows that carbon dioxide emissions have increased from less than 5 billion tons in 1850 to more than 50 billion tons in 2023. Additionally, this image shown to us by NASA GSTEM shows that the global surface temperature has increased from less than 0 degrees Celsius in 1850s to more than 1.5 degrees Celsius in 2025. This doesn't seem like a large increase, but believe me, it's a lot, and it's hitting our temperature, our Earth, to such extent that ice glaciers are melting at a rapid rate. So, why does this happen? Well, majorly because CO2 emissions are increasing. The CO2 emissions have increased from 280 parts per million in pre-industrial age to more than 380 parts per million. And currently, it is increasing at a rate which is more than 2 ppm per year. Well, there are many contributors to CO2 emissions, but the biggest one of them all is the transportation sector, which contributes to 24% of the total CO2 emissions. So as a result, my invention reduces CO2 emissions in automobiles. Now this is a schematic diagram of an automobile, which shows its diesel tank, its internal combustion engine, then a DOC and DPF, which is known as a diesel oxidation catalyst, and a diesel particulate filter, which is used to reduce carbon monoxide and hydrocarbons into pure carbon dioxide and water, while DPF is used to trap carbon particles, and the selectocatalytic reductor, which is used to reduce nitrogen oxides into pure nitrogen. So till now, it's a classic schematic diagram of vehicles, but now we will be introducing my innovation after SCR. So this will be a sprinkler-based system which will sprinkle sodium hydroxide onto the exposed carbon dioxide emissions, which will lead to formation of sodium carbonate and baking soda, leading to reduction in carbon dioxide emissions in vehicles. So I am explaining this in more depth in the process flowchart of my system. So first, when you will start and drive the vehicle, there will be these sensors present inside it, which will record the VCECT parameters, which mainly include sodium hydroxide levels, sodium carbonate solutions, temperature, and other engine parameters. Then, as the carbon dioxide emissions will reach the end point of SCR at here, then the injector sprays will be activated, which will release sodium hydroxide. This sodium hydroxide will react with carbon dioxide and lead to formation of sodium carbonate. This sodium carbonate will be stored in sodium carbonate tanks present below for my system at this place. And there will be sensors which will record the carbon dioxide still present after the reaction. If the carbon dioxide ppm is more than the requirement ppm, then it will spray additional sodium hydroxide through spray injectors to reduce its amount. When the requirement amount is reached, then it will monitor CO2 parameters, sodium hydroxide levels, sodium carbonate filling levels, exhaust temperatures, and other engine parameters. And then it will continue for the next driving cycle. However, if the sodium hydroxide spray injectors were not activated, then it will run a background check to see if there are any empty sodium hydroxide tanks, or if the spray injector is faulty, or if sodium carbonate saturation tanks are completely filled. If the answer is yes, then it will give an indication on the instrument cluster about the faulty spray injectors or filled sodium hydroxide solutions or empty sodium hydroxide drivers, and it will advise drivers to go to fuel stations or service centers to rectify this issue. And as a result, the entire loop will continue. So there are a few salient outcomes of this entire process. Firstly, there will be a direct industrial use of sodium carbonate. The sodium carbonate, which will be collected, can be used in multiple industries which include glass manufacturing, water treatments, and detergent productions. Additionally, this system is very simplified as we are not using any regeneration of sodium hydroxide in our vehicles. It is very energy efficient and it's very easy to implement. Additionally, fresh NaOH can be supplied to vehicles while sodium carbonate can be sent to industries, thus creating a streamlined circular economy. Lastly, we are reducing carbon dioxide emissions in the vehicles. As sodium carbonate we are repurposing it for industries, we will be reducing carbon footprints in both transportation and industrial sectors. So these are a key few technical highlights of the invention. Firstly, we will be using sodium hydroxide to capture carbon dioxide from vehicular emissions, and we are converting it into usable carbonates, namely sodium carbonate and sodium bicarbonate. Then the effectiveness of this entire process really depends on sodium hydroxide's concentration and the chemical reactions which takes place. On a nutshell, this entire process consumes around 2 moles of sodium hydroxide for every mole of carbon dioxide captured. Then, if there are any wet conditions or production of water in the process, then the reaction can proceed further and it can lead to formation of sodium bicarbonate as shown in this diagram in this reaction below, and it requires only 1 mole of sodium hydroxide per mole of carbon dioxide. As these carbonates, namely sodium carbonate and sodium bicarbonate, have very low energy states, that is 60 to 180 kilojoules per moles, when compared to carbon dioxide, which is 400 kilojoules per moles, the energy released will be quite less, and thus it provides a stable and secure carbon sink. Lastly, the nitrogen dioxide emissions can increase by 15%. As this reaction is an exothermic reaction, there will be release of energy and heat, which can reduce the efficiency of selectocatalytic reductors. As a result, my invention needs to be installed after SCR or nitrogen dioxide trap systems in order to increase this efficiency. Now I will be explaining how my entire invention undergoes circular economy. So there will be two major tanks present inside the automobile. First one will be a sodium hydroxide tank and second will be a sodium carbonate storage. As the vehicles will go to fuel stations to refill their diesel tanks, there will be sodium hydroxide filling pumps, which will provide fresh sodium hydroxide to the sodium hydroxide tanks. And there will be a sodium carbonate collection centers, which will take the produced sodium carbonate from the storage tanks, and then they will be transported to causticization process plants, which will process them and create sodium hydroxide, compressed carbon dioxide, and construction materials. As in the carbon dioxide, which was generally released from vehicles, is now converted into compressed carbon dioxide, we will be effectively creating a circular economy. As pure carbon dioxide cannot be used for many purposes, while compressed carbon dioxide can be used in various industries, for instance, in fire extinguishers. So now these are a few technical highlights of my invention. Firstly, my entire ecosystem requires sodium hydroxide supply and sodium carbonate collection centers. Then it requires transportation networks and causticization process plants. The fuel station needs to be developed a connection and delivery ecosystems, as it can collect this mixture from all vehicles and transport them to causticization plants. This produced sodium carbonate can be emptied in every interval of 500 kilometers, which is quite aligned to the amount of kilometers fuel such as diesel can run on. So drivers can sell off sodium carbonate and fill up sodium hydroxide at the fuel stations. Lastly, recovering sodium hydroxide from sodium carbonate requires a two-step precipitation and a crystallization method, which needs to be performed in industrial settings and cannot be done in the vehicles. So now I will be explaining the entire regeneration of sodium hydroxide. So first, 1 kg of sodium carbonate and 8 liters of water will undergo electrolytic regeneration, which will lead to formation of 0.35 kgs of carbon dioxide, 4 kgs of sodium hydroxide, and 4.5 liters of water. These 4 kgs of sodium hydroxide will undergo evaporation and it will lead to formation of 0.65 kgs of sodium hydroxide and 3.35 liters of water. So in the end, the recovered sodium hydroxide can be recycled and used again in vehicles. Then this sodium carbonate can be used to make multiple products also. So, such as it acts as a washing soda also and acts as a soda base also. Additionally, it can be used for construction materials as well. Lastly, this is a carbon negative or carbon neutral production system. As this carbon dioxide won't be released outside, it will be compressed and used in various industries such as fire extinguishers. So these are a few key advantages of my invention. This invention will capture millions of tons of carbon dioxide annually from transportation sectors. It will provide valuable materials for industrial uses such as sodium carbonate and compressed carbon dioxide. Secondly, it can directly lower greenhouse gas emissions as we are capturing the exposed carbon dioxide released from vehicles and converting it into compressed carbon dioxide. And thus, it can combat global warming. Then it's a circular economy as we are converting carbon dioxide into sodium carbonate, which is useful for various industries as mentioned before. And it can be implemented very quickly. Our system doesn't require much of time as it generally just requires a few procedures which can be implemented in current existing vehicles as well. Additionally, because of this, it can allow drivers to continue enjoying the convenience and the familiarity of petrol and diesel vehicles. Lastly, it provides long-term viability. Even though electronic vehicles are becoming very popular, this system can be still used in commercial fleets such as trucks and long-term distance vehicles. So now I will explain a few key challenges of my invention. Firstly, the entire materials which will be required to build this system will increase the cost by around $2,000 and it can increase the weight by around 15 to 18 kg, which is quite less when compared to the actual weight and cost of vehicles. Secondly, the carbon dioxide capture system needs to be compact and safe packaging in vehicles as it does not need to be like interact with other capture systems such as SCR or dioxin. Then it should be thermal efficient materials should be used as this process from sodium hydroxide to sodium carbonate is quite exothermic in nature. So there doesn't need to be any overheating issues happening inside the vehicles. Then there needs to be development of few infrastructures. As in every fuel station, there needs to be a development of sodium hydroxide by producing stations and sodium carbonate collection centers. Then this entire system needs to be adopted by the public. As drivers, we have to ensure that drivers are willing to regularly empty the sodium carbonate tanks and participate in recycling processes. Lastly, this entire recovery process requires electricity and heat energy, and this has to be done in chemical process plants. In order to reduce carbon emissions, renewable energy sources need to be used to supply electricity and heat. So there are many global drives and policies which have been used to control greenhouse gases. For instance, the 1988 World Conference, Kyoto Protocol, and Paris Agreement all aim to reduce carbon dioxide emissions and some all aim to reduce carbon dioxide emissions while keeping the surface temperature under 1.5 degrees Celsius. And the post-2020 framework have provided specific goals for countries, such as the European Union has to reduce the carbon emissions by 40% by 2030, the United States of 26 to 28% by 2025, China by 60 to 65%, and etc. by 2030. So in conclusion, my entire system provides a cost-effective and environmentally friendly solution that addresses the needs for automobile manufacturers and drivers who mainly prefer petrol or diesel cars, while it still contributes to reducing CO2 emissions. Also, it allows for continuous use of existing infrastructure. As we are providing an immediate impact on reducing emissions, it can act as a key transitional technology on a path towards a cleaner future. Lastly, this approach can appeal to both environmental concerns and practical realities, as it can allow us to reduce carbon dioxide in all types of vehicles and machines that uses internal combustion waste power generation system. So these are few references that I used for my entire research paper. Thank you.